Hello, it's me, and you find you have a hankering for triangular type puzzles, pyramidal type puzzles. And luckily one is now mass produced, which is this guy over here, this Megamorphix puzzle. Now before, when displaying this was only as something very rare made by Tripoom, but now this is mass produced. Here's other versions. This is a master Tetrahedron, which looks like a Jinx Pyraminx, but the master version of it. Well, I've always wondered why it was called the master, because this is 1, 2, 3 layers, where this one, which is I think the Professor Tetrahedron, is 1, 2, 3, 4 layers, which is the next step up above this. So maybe this guy belongs here because this is 4 layers, just like this is 4 layers. But this one seems to have more of a symmetry with that. I always thought that this looked kind of interesting. You got 2 centers here, then you've got that which surrounds it, and then corners over here as well. This is another Tripoom product, and this is the Rex puzzle. So this is a Rex Tetrahedron. All of which fascinating puzzles, but in any case, so you've got this puzzle here and you want to know how to solve it. Well, I did go through a demonstration of this at one point, but it was more of a demonstration than a tutorial, and the other issue is what to do with the parities with this. So what I'm going to do is I'm going to go through a description on how I solve this puzzle, and then address the question, what about the parity? Is there a way to dispense with all parities and solve this without that? So here's the standard way of doing it first. Abracadabra. Okay, so we've got ourselves what looks like a nice little scramble here. Now, the way that I'm going to go through this, just to help clarify some of the concepts that we're going to have to be unpacking as we're doing this, concepts such as parity and false equivocation and all that good stuff, I'm going to be making use of its little cousin, the Master Morphix. I'm also going to be making use of a standard 4x4 and 3x3, because to do this, you have to know how to solve a 3x3, have to know how to solve a 4x4. Probably a good idea to know how to solve one of these guys here as well, so that we can show exactly what's going on with the nature of the solve. So let's go ahead and actually scramble these other puzzles so that this can make a lot more sense. Okay, so we've got ourselves a whole mess of scrambled type puzzles. So the first step with this is, well, how do you want to solve this? Most of the time when people think about solving a 4x4, which is what this is they do it by reduction. Let's reduce it. Let's reduce this scrambled 4x4 to a scrambled 3x3. And then upon reducing it to those puzzles, solve it as such. Well, here's the issue with that. A 4x4 puzzle is not a 3x3 puzzle. As a matter of fact, it has a different parity. So every puzzle has a parity, which just means is it odd or is it even. So these are even layer puzzles, these are odd layer puzzles. These have even layer parities and odd layer parities. What's the basic difference between that? And why do we even identify a different characteristic? Well, the basic difference is I can see all of the pieces of a 3x3. They're all in front of me. The only piece of a 3x3 that I don't see is the 1x1 deep inside. That 1x1 is actually the core, deep inside over there. So there you have it, but I can see all the pieces, centers, edges, and corners. I can see that. This Master Morphix is a 3x3. Basically, it's a shape modification of this. So this move here is equivalent to this move here. But inherently, being an odd layered puzzle, I can see all the pieces. I see the centers, I see the edges, I see the corners. And I can do the same thing. The only piece that I don't see is I don't see the edge deep down inside. And I'm not going to take this off, but basically that's how it is. I see all the pieces here, I see all the pieces here. That's what makes it odd layered. That's what gives it an odd layered parity. It just means that I see all the pieces. An even layer puzzle has a slightly different meaning. There are pieces that I don't see here. If you were to take this apart, what you would see is that these pieces that I'm calling a center are not really centers. You've got an inner piece here that you can maybe just see. See where that screw is? Well, there's a center piece here that you don't see. It's hidden. You can see it, say, over here. This is Tony Fisher's inspired globe cube. But basically this is a 6x6, another even layered parity puzzle. And what you can see is this piece here, which is covered up by here. So you can see as I'm moving this around, this piece here doesn't move. This is the true center. As I'm turning this, this rotates. So hidden inside a 4-layer puzzle are the hidden pieces. So these are not the real centers. This is the real center. These edges, these are not the real edges, no more than these guys, these guys are real edges. These actually are corner pieces, specialized corner pieces. Deep inside here is a hidden edge piece. That's these guys. These are the hidden edges. And you can tell that because if I just move, say, well, luckily we've got black ones, we've got white ones, but I move the white one down here. If I just move this, and I move this down, you can see that this edge piece moved along with this. This is the real edge piece. These here, all the pieces that surround edge pieces are called corner pieces. So these are really more like corner pieces than edge pieces. I can move this back over here. Let's move this one. Well, if I see which piece moved here, it's the second one down. So this is the true edge piece that moved along with all of these specialized corner pieces. Let's move this back, and now if I just move this, as you can see, this stayed the same, this stayed the same. This collectively becomes the the edge pieces. So basically, we'll move this back over here. So basically what that means is that an even layer parity just means that the true centers and true edges are hidden. They're underneath, which makes all of these pieces on an even layer puzzle really just specialized corner pieces. Corner pieces are on either side of an edge, and they also join three faces. Well, so too, all of these pieces are on either side of well, a corner here, of a center here. So you can say that these are really just central corner pieces. And these guys here, what we call edges that we reduce as such, aren't really edges. They're on either side of the true edge underneath, which looks like this. So in that way, they resemble more like corners. So if I had to broaden it out even further, then I would say that a puzzle that has odd parity has all of the pieces here seen and available for use, available to be seen, basically. That's what an odd layer parity means. An even layer parity means that all of these pieces I look at as specialized corner pieces that are over the actual center pieces and edge pieces. So an even layer parity puzzle has hidden centers and hidden edges where everything is specialized corners. So that's the inherent difference between an even layered parity and an odd layered parity. So how does that impact the solve? Well, if you're going to reduce this to a 3x3, you're reducing it, you're changing the parity, so to speak, from an even layer parity with hidden pieces to an odd layer parity. We're now going to call these centers once we reduce it. We're going to call these edges, and then we're going to solve it as an odd layer puzzle, hoping that it'll make sense. But in reality, if I flip an edge here, I'll see it. I'll know it. I'll be able to recognize it. I won't continue with the solve. If I flip an internal edge here, I won't know it. But I'll end up with an impossible situation that I will not be able to solve as an odd layer puzzle, which renders that as a parity problem. So a parity problem will occur if, and only if, I take one parity, even, reduce it to another parity, odd, try to solve it as that odd, and find myself unable to continue. And the only way to continue is if I do a flip by moving two pieces, by exchanging these two pieces and then calling it a re-reduced puzzle. That's a parity problem, and it only means that the hidden pieces on the inside rendered me unable to see where I was supposed to reduce these to. So that's what parity problem means. If there's any other questions on that, let me know. I can try to further elucidate that. But that helps me in terms of solving, because when solving something like this, I need to recognize, do I have a parity problem because I reduced it to this, but it's not quite making sense? So the first step is, well, let's get our perspective. Here's our centers, right? And here's our edges, and here's our corners. So this is going to resemble, in this state, more of a jumbled up cube than an actual pyramid. So the first step is to go ahead and reduce these. The reduction of a 4x4 is the simplest thing in the world, actually, because all I have to do is take all of these equivalent pieces. All these centers are equivalent to each other. I can flip them, I can rotate them, I can exchange them, and they look exactly the same, and they behave exactly the same, so I need not worry about any of that. So see what I just did? I just reduced this 3x3. Now I have to know what centers go where, right? Now if you have the color configuration memorized, that's no problem, but let's say we don't. Let's say we have a different thing here, so I can move this up and I can say, okay, yellow goes here, red goes here, easiest thing in the world. Go ahead and continue our reductive process. Boom. Okay, so I got yellow here, green here, I put in the red one here. Once again, no worries. Now I've got red. So now I can let the corners guide me regarding the rest of the puzzle and be able to easily place everything else that needs to be placed. For instance, orange needs to go here. Lickety split, I just put in for the orange and move it in. Again, assuming knowledge on how to do this. Okay, so the edges were the centers were very simple to place in because all these are equivalent. What if I flip these two? Will that mean anything? Not really, because they look the same. I'll go ahead and flip it. I'm just doing a corner swapping algorithm. I swapped it and it doesn't really mean anything. Okay, so I swapped these two, but you wouldn't know it. Actually, I didn't swap it. This went to here, this went to here, and this went to here, but you wouldn't really know it. Now notice when I swapped it, I used the corner swapping algorithm because, well, these are really corners, not centers. But now I'm going to say, yep, these are now centers. These are 3x3, bona fide 3x3 centers, and what I'm going to do is I'm going to reduce these edges just like this one is reduced here, and by reducing the edges, I'll have turned myself into a 3x3 and no worries. Even though it's a different parity puzzle, but I won't tell if you won't tell. Anyway, to reduce it, as you recall, this edge goes down here, sacrificing one on the top here. So I'm going to take this edge, match it up, bump it out of the way, put this one in its place, put it back up to put the centers back in. And I do this all around the puzzle, well, like this. Okay, so now I have myself down to the last two edges. These two, I don't have another one to sacrifice, so I do an algorithm that puts this to here and this to here, but I don't want to do that because I'm going to end up in the same situation. So this will come down to here to match with this white, this will come up here. The way to do that is put it to the side, then do R, F, I, U, R, I, F, and bring it back in. Okay, so what I have now is I have myself a reduced 3x3. So the solve is pretty much the same. So what I'm going to do is I'm going to take this puzzle in its scrambled form and turn it into this puzzle in its scrambled form the same way that I did with this. Now, in some ways it might be a little bit more hard because these centers were completely equivalent. These are not equivalent. I got different sides. So I've unpacked the notion of what parity is. The parity is even or odd. Are we revealing all the pieces or do we have hidden pieces? Now I'm talking about equivalencies of pieces. We see equivalencies of these. This has translational equivalency where this can plop to here, this can plop to here, and this can plop to here. It also has a rotational equivalency. If I were to rotate one of these pieces, which I can't do, but if I could, you wouldn't know the difference either. So translational equivalency and rotational equivalency. I haven't talked about any problems with those yet, but those are different concepts. Each piece can have equivalency with another piece. The puzzle as a whole has a parity. So I have to bear in mind the puzzle as a whole having a parity and each piece having potential equivalencies. Okay, so let's do the same thing that we did here, but I'm going to slow it down a little bit to do that. So the way that this is going to work is, well, let's start with the center. I'm going to start with a green center. Now, unlike this guy, it's not defined where the center locations are. But here is a green and yellow, and the way to reduce the centers here is I want to match it up with a solid yellow or solid green on whichever side. It doesn't matter which one, and I've got a couple to choose from. I have equivalencies, here or here. Now this is already delivered to us in this configuration, so let's start off with this. Now if you have one that has a green next to it, the other center that has the same color scheme will have to have the other color, in this case yellow. So I'm going to have to put a yellow into here. So here's a yellow. Let's bump this out of the way. And I'm going to take this yellow, put it down here. Now that I have these matched up like that, I'm now going to put it into the same side like kersplat. And this is what it's going to look like. These are across from each other, these are across from each other. So now what goes next? What goes where? Well, I'm going to use my corners to guide me. So let's match this up like so. So I've got green here and yellow here. This will tell me what's supposed to go next. If I focus on the green, then down over here I'm going to have green and blue. So green and blue is going to be here. So I know that's supposed to be there. So I'm going to look for the green and blue, because green is here. This is a green and a blue, so that's going to match with this. Here's green and blue. So what I'm going to do is I need to match, either put a blue here or a green here. Doesn't matter which, but it's got to be one or the other. And I've got to put it up over to here. Here's a green that's already in. So what I'm going to do is I'm going to match this up with a green. I'm going to see how it's going to fit. This is going to come up here. And this is going to come up here. Okay, so I'm going to take this and put it into this slot over here. So move it up. Now I got to move this one back, right? So I'm going to bat this down out of the way and move this back down. Okay? So I've got the blue and green. I'm going to find the other one, but match it with a blue side, a blue solid one, as opposed to a green. So where is that? Green and blue, right over here. So I'm going to match it up with a blue and then put it into here. So where's a blue? Could be any one. Here's one right over here. I'm going to put it to here. So move it down to match it up. Let's bump it out of the way. I'm going to move this back up over here. Now that I have that in, I've got to move it into this center slot. The way that I'll do that is I'm going to take this, cast it down, double turn this, move it up. Now I'm not doing anything different from this side. I'm just getting the pattern right. Now that I've got that in, let's go ahead and match up the centers just so that we don't get confused. Yeah, so we like that. We've got green here, yellow here, blue here. Okay, so remember this is our top, so what's going to come here is the only green that's available, and that's going to be green and red, so that's here. So what we're going to do is we have to match this green to a solid green here or red here. Doesn't really matter which, but here's green here, so I'm going to take this, move it into place, bump it here, and bring it back. So we've got this over here. I need to find the other blue and red and green rather, right over here. This is matched up with a solid green. I need to match this one up with a solid red, which could be any one of these. Which one? Doesn't matter. Any one of these three will do. So we move this in, bump it out of the way, move this down. Now I need to move it up to here. So move this down, double turn, move this in. Okay, so let's line this up over here. Remember this was on top, so we've got these over here. I'm going to make use of my corners once again. Let's get this lined up right. Just doing RIDA, RD until I can line this up correctly. Turn this across here. Nope, not yet. And here. Okay. So this is all good. This is all good. So now the question is what's supposed to go where? Well, we can take a look here. This is supposed to be yellow and red. This over here is going to be the yellow and red side. So now that I have all these in, the others I should be able to derivate based on the corners. So this is yellow and red is supposed to be here. I've already got this one in. I got to move a yellow one here or a red one here. Here's a red one, so that's easy to do. Which one? Any one. So I'll move this in, bump it out of the way, move it out. Okay, where's the other yellow and red? Right over here. This one is matched up with a red, so I must match this one up with a yellow. Which one? Well, one of these. So what I've got to do is bump this out of the way, move this in, put this in place over here. Now I'm just going to match it to here, put this down, and bring it up. Okay, so now this is it. So now where can we go from here? Well, we can look at this one. It's the only yellow one available. It's got to be yellow and blue. Down to the last two centers. Now with the last two centers, don't sweat about the other one. Just put one in that is, just put one in and then we'll worry about the other one later. So let's match this up with, say, a yellow. Here's a yellow here. move it down, turn, move this up. So now I need to match this one up with the blue. Here's a blue here. So move this up, turn, and move this down. So now this is in. Now that this is in, we look over here. All the pieces are where they need to be, but you can see it's not assembled quite right. So what do we do about this? Well, again, don't sweat it, just figure out what has to go where. As you can see, this is in right, this has to be swapped. Now I said before that a puzzle that has even layer parity is pretty much a corners only puzzle. So I can just do a corner swap with this, and that's what I'm going to do. So put all of these guys in. You can even match them up if you want. You're pretty much done. This one is just a matter of doing a corner swap. So let's go ahead and corner swap these two. The way that's going to work with a corner swap is we're going to be using this layer and this layer up here, but the corner swapping algorithm is, and this is going to be my R move, 2R U, 2R UI, 2R, then we do a UI and a D, then finish up with 2R, UI, 2R. U, 2R. That'll swap that. This can move back, and you won't touch this here. So don't sweat it. It's no real problem when you're dealing with super cube, super 4x4s. If you see one needs to be swapped, just go ahead and swap it. So there you have it. So all the centers are in just like you had here. Edge reduction is even easier than this because you have equivalent pieces. So this is already in, this is already in. Chances are you're going to have some that are already in. Just don't lose your perspective. Remember, don't look at this as a tetrahedron, as a pyramid, because it's not. It's a cube. So now what I want to do is I want to move, say, a red one into here. And take your pick. This to come into here. I'm going to sacrifice this. So we'll go down, bump it out of the way, move this down, turn this across, and move it back. This, well, can find a home here, but it's already found a nice home here. So I'm going to move this into place, down. So this is that same algorithm, and up. So no worries. Let's see, what else is going to go where? Well, we can move this into here, down, bump it out of the way, move this in its place, move it up. So right now, really not much of a difference than a usual 4x4 solve. Okay, I want to move this green one in. So this will move down here. So down to sacrifice this, bump it out of the way, put this one in its place, this comes in, and look, I put that one in too. Okay, this is going to come down to here. Any of these that aren't in? Nope. But this one is, so very quickly you can do a nice quick reduction with this. This comes down, turn, 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 up, and now this is in. So moving around, you see that we have reduced all of the edges. Now you might have ended up with another situation where you have just two that are out, and that would look something like this. Well, something like this. So everything is in, and you can see that these are the last two. So what you want to do is you just want to flip these with that same algorithm. So once again, you move it to the side, and you do R, FIU, RIF, and move it back. Okay, so now what we have is we now have taken one parity and converted it to another. We took an even layer parity, turned it into an odd layer parity, and now we basically have ourselves a scrambled 3x3, right? 3x3 version. So we just go through the process of solving it as a 3x3, which looks a little something like this. Okay, and that is the closest I'll ever come to speed cubing. But in any case, I'm going to leave this. Go for now. So this one we solve it the same way, like this. Okay, so I'm going to leave this go as well. I'm just going to save that last layer for later. So basically, if you know how to solve this, then you're going to proceed the same way by solving this guy. But in any case, the first thing that we can do is we can go ahead and match up the centers, like so. And it's looking more like a triangle already. And so too, we can match up these centers here. Our non-reduced centers, and we are foolishly thinking that these are the same kind of puzzles, solved exactly the same way. Remember, one is a different parity than the other. So we can't exactly solve it the same way, but maybe it might seem like we can. Okay, once these are lined up, what we're going to do at that point is we're going to get the cross. So by getting the cross, we see that this is in and this is in, and now we have to move these guys in. And I can go ahead and get this to the last layer as well. Okay, so we got ourselves down to the last layer here. So let's go ahead and slow it down a little bit and start doing this. So this is in and this is in. So we're going to find the other green side here. And I'm not doing anything different than I would do with the 3x3 version. So I'm just moving this to here, bringing it on up. And now for the orange, the yellow rather, this will come here, wrong side. So what I'm going to have to do is bring this up. Now if this part's confusing to you, I'm really just doing a 3x3 solve, so you're just going to have to kind of watch and make it make sense. So this is all here. Now I got to put these corners in. So this one I'm looking for the red, yellow, and green, which is in the wrong place here. So I'm going to roll it in. Now notice I have a pretty specific position that has to go in. So as you can see, this is not correct, right? So it has a specific rotation. It's not equivalent on all sides, and now that's in. Now what about the yellow one? Well, I need the little yellow piece here, but this one can go in any direction. So I move this in and I'm done. But I can move it, I can rotate this any direction and it'll be the same. So this I had to work to put in, this one I didn't. This is equivalent in terms of its rotation. That's going to become important later. So bear in mind, the parity of the puzzle is the overall organization of the puzzle being even layered. The rotational equivalency has to do with a single piece, or the translational equivalency has to do with a single piece and its ability to swap with another. So I'm looking for the proper one here, which is hidden up here. So that's fine. And now I move the green one in. Turn, turn, and turn. Turn this upside down, and now I'm going to go ahead and put this layer in here. This is the right color, wrong place. I'm going to swap this one. Now notice in a 3x3 I couldn't use just any edge, but here I can. So this one is yellow, so I'm doing a beginner's technique of putting this edge in. I'm not going through that algorithm because I'm assuming knowledge with that. I'm just pointing out the equivalencies as I'm doing this. I'm looking for green. Green doesn't come in this direction, it comes in this direction. Okay, so now we have ourselves to the last layer.